Good morning, students. Let us start the class now. We had solved this exercise yesterday regarding the base bias, and we had seen how this input impedance and output impedance and voltage gain are computed. And I was telling you yesterday, ideally any amplifier should have a very high input impedance, very low output impedance, and it should have a very high voltage gain. But ideally any particular circuit does not exist. So practically what we do is we cascade many configurations. For example, in common emitter we will get this voltage gain, whereas in common base we will get something else, and in common collector we will get something else. That I am going to show you anyhow in the future exercises. So in general what we do is we combine many of such configurations to get this ideal behavior, because in a single circuit all these ideal behaviors are not achievable. So you can see in this particular circuitry, input impedance is supposed to be high, but it is actually very low, only 1.07 kilo ohms. Output impedance is supposed to be very low, but you can see that it is higher than the input impedance itself. Whereas voltage gain is at least satisfactory, 265 times voltage gain is there. So this was the discussion of the base bias yesterday. Let me continue today's class. Now whatever circuit you are seeing here at the left side, this is basically emitter bias, which we had seen earlier. The Q point of this emitter bias or self bias is more stable than that of the base bias or fixed bias. Now if we go for AC analysis of this particular circuitry, you can compare the upper circuit and the lower circuit together, and there is a RB, here also there is a RB, there is a RC, here also there is a RC, there is a blocking capacitor and a coupling capacitor. In addition, there is an emitter resistor here in the emitter bias circuitry. But when we go for AC analysis, I had told you about this particular bypass capacitor. Its purpose is to keep the Q point very much stable even when the input signal is applied, so that AC signal will not remain at emitter at all, only the DCVE will remain. If at all there is any AC voltage at the emitter, that will be bypassed to ground. So the purpose of the bypass capacitor I had discussed earlier. Now when we consider this bypass capacitor, emitter is directly connected to ground because all AC is passing through capacitor. So when we write a model for this emitter bias, it will be same as the base bias. So the AC analysis of emitter bias or self bias is same as that of the base bias or fixed bias. That's what I am going to tell you now. AC analysis of self bias in common emitter configuration. As the bypass capacitor shorts the emitter resistor, the AC analysis will be same as that of the fixed bias circuit. So we are not going to deal with the emitter bias separately as far as AC analysis is concerned. So now let me proceed with the AC analysis of voltage divider bias. Now this is the circuit with R1, R2, RC, RE along with the blocking capacitor, coupling capacitor and bypass capacitor. How do we write the AC equivalent circuit for this? Capacitors all short and VCC is AC ground. Anyhow DC ground itself is AC ground at the lower side. So we can replace all the capacitors with the short circuit. R1 and RC can be connected to ground. R2 and even emitter can be connected to ground, because emitter is bypassed to ground by means of this bypass capacitor. So the circuit becomes like this, except the replacement of RB with R1 parallel with R2, all the other parameters remain the same as that of the fixed bias circuit. You can see RC other end will be connected to ground, emitter will be connected to ground because of CE, and instead of RB we have R1 and R2, but again R1 other end is connected to VCC As far as AC signal is concerned, it is AC ground and R2 is anyhow ground. So at the input we will have R1 parallel with R2, then RC connected to ground and emitter connected to ground, and the transistor is replaced with its Y model or RE model. In this manner, now this is the equivalent circuit for voltage divider bias. You can see that the highlighted portion with blue color is nothing but the transistor's RE model. At the input we have beta into RE, at the output we have the current source IC is nothing but beta into IB, and we have a output resistance R0. Later on, RC one end is connected to ground, so RC is parallel with R0, and at the input R1 other end is connected to ground, so R1 and R2 are in parallel. So except for this R1 and R2 that is in parallel, all other things are the same as that of base bias circuit. Now based on this, we can easily write the expressions for the input impedance, output impedance and the voltage gain. You can easily find out the expression for the input impedance, that is nothing but R1 parallel with R2 parallel with beta into RE. And you can easily find out the expression for the output impedance, that is nothing but RC parallel with R0. And for the voltage gain, it is nothing but V0 divided by Vi. So that we will see in the next slide. Now, as all other things are remaining the same, except for that R1 parallel with R2, all other expressions for the voltage divider bias are going to be the same as that of base bias. So let us proceed directly for an exercise. You can see this exercise where beta is given 100, R0 is given 50 kilo ohms, and all other capacitor values are given. Now let us proceed with the calculations. Initially we have to find out this small Re or the dynamic resistance of the emitter. If we have to find out Re, then we have to find out IE, because Re is nothing but Vt divided by IE. That Vt is the thermal voltage, which is 26 millivolts at 27 degrees centigrade. This we already know. So how to find out Re? We have to find out IE. How to find out IE? Either we have to go for a approximate analysis or we have to go for a accurate analysis now. Now there is a condition that this beta Re, if it is greater than or equal to 10 R2, then the approximate analysis is satisfied. So what we can do is, please recall whatever we had discussed during DC analysis. What we can do is, we can immediately check for the condition, whether that condition is satisfied or not. If the condition is satisfied, we can directly proceed with the approximate analysis, ignoring IB. So let us see. Checking for this particular condition, beta into Re must be greater than or equal to 10 R2. Let us check it. Beta is given as 100. This capital Re is given as 1.2 K. So total it is 120 K. It is greater than 10 R2 because R2 is 4.7 K. 10 into 4.7 K is 47 K. 120 K is greater than 47 K. So we can directly apply approximate analysis, ignoring beta and ignoring IB for calculating IE. So using approximate analysis, VB is 4.7K into 60 divided by 43.7K. What is this 4.7K? VCC into R2 divided by R1 plus R2. VCC is 16 volts into R2 4.7K divided by 39K plus 4.7K. That is 43.7K. So we get VB as 1.72 volts. When we get VB as 1.72 volts, that minus 0.7 is going to be IE. So IE equals 1.72 minus 0.7 divided by RE 1.2K. So we get VE here. VE is nothing but VB minus VBE. So 1.72 minus 0.7 divided by 1.2K, we get the value 0.85 milliampere. When we get IE, we can easily find out RE. 26 millivolts divided by 0.85 milliampere equals 30.59 ohms. So we got this RE now. We can easily find out input impedance is nothing but R1 parallel with R2 parallel with beta into RE. Now, students, can you quickly tell me the answer for Zi? Quickly calculate R1 parallel with R2 parallel with beta RE. Now you know the value of small re. Multiply it with beta. Beta is given as 100. Now calculate the value of 39K parallel with 4.7K. Then that value parallel with beta into RE. You people quickly calculate and tell me the answer in the chat box. I'm waiting. Okay, Lokesh Biswas has given the answer 1.7 kilo ohms. Any other answers? No other answers. Only one student, Lokesh, has given me the answer. Anyway, let me proceed with the exercise now. Zada is 39K parallel with 4.7K parallel with 3059. It is 1.77 kilo ohms. So Lokesh, good that you gave me the answer, but in general, always go for 2 decimal points. In general, in electronics, we generally go for 2 decimal points precision. Now, can somebody again tell me quickly the answer for Z0? Output impedance is RC parallel with R0. R0 is given 50 kilo ohms, RC is given 3.9 kilo ohms. I want somebody to tell me the answer. Students, whenever you listen to the lectures, you should always have a notebook with you. You should always have a calculator with you. You have to be attentive and you have to be working out. Otherwise, later on, you will get confused with everything. So, Lokesh Biswas again has given me the answer 3.6 kilo ohms. No other student has given me the answer. So, let me find out. Z0 is 3.9K parallel with 50K, that is 3.62 kilo ohms. Good, Lokesh, you have given me the correct answer now. Now, what is AV? AV is RC parallel with R0 divided by RE. That RC parallel with R0 is already there as Z0 here. So, voltage gain is nothing but 3.62K divided by small re. Small r is 30.59. So, okay, Sayan has given the answer as 2.033. No, something wrong. It cannot be 2.033. Voltage gain in case of common emitter will be much higher. 3.62 kilo ohms divided by 30.59 ohms. That means 3620 divided by 30.59. So answer will be larger. Let me show you the answer. 3.62 kilo divided by 30.59 is 118. That is going to be the voltage gain. So you should have a general idea. Whenever you work out such exercises, you should have a general idea that you will get Zi always lesser than Z0 in case of all these common emitter configurations. You please remember that. And you'll always get AV more than 100. This also you remember. If at all during the test or during the exam, you should get values like this only. You will generally get Zi less than Z0 and you will get AV more than 100. If you don't get those values, then you will have to verify your formula or your substitution or your calculation again, because the answers can be drastically wrong. Please remember this. We have been discussing base bias and we have been discussing voltage divider bias now. In both of the cases, Zi will be smaller than Z0 and AV will be larger than 100. You will have to remember this. Now, in some cases, the manufacturer may not give this R0 at all. Or even in the textbooks, when they give some exercises, they may not give this R0 at all. Imagine if R0 is not given, then how to solve the problem? If R0 is not given, then we should assume that R0 is infinity, because R0 cannot be 0. The output resistance across collector and emitter, it cannot be 0. Actually, the output resistance of the transistor, which will be much larger, we are already seeing it is 50 kilo ohms, whereas the value of the collector resistor is quite smaller. So when we compute Z0, 3.9K parallel with 50K, we get around 3.62 kilo ohms. Now, if 50 kilo ohms is not given, then we have to assume that it is infinity, because it cannot be 0. So, if R0 is not provided, then Z0 is 3.10 kilo ohms parallel with infinity, that is again 3.10 kilo ohms. Whenever two resistors are in parallel, generally the effective resistance will be lesser than the smallest resistor out of them. Now, in these two cases, as one side is infinity, Z0 is naturally 3.10 kilo ohms itself. That is Z0. Zi will never change here. If R0 is not given, we have no use of R0 with Zi. What about AV? AV is directly 3.9K divided by 30.59 is around 128. So, AV slightly increases if R0 is not provided. I hope you have understood this. Let me proceed with the next slide now. We are going now to this analysis of the common collector configuration. You can see on the slide now, this is the analysis of common collector configuration. In the common emitter configuration, we discussed only two. One is base bias and voltage divider bias. We need not discuss emitter bias because it is same as the base bias as far as AC analysis is concerned. Now, this common collector also we had discussed earlier, and we had done only the DC analysis. Now, the AC analysis of this circuit is slightly different, because we are taking output at the emitter and there is no bypass capacitor here. In this circuit, there cannot be a bypass capacitor at the emitter, because if at all there is a bypass capacitor from emitter to ground, then all the signal which is at the emitter will go to ground. That is nothing but output itself will go to ground. So, this common collector configuration will have only blocking capacitor and coupling capacitor. It will not have a bypass capacitor. And this is basically a base bias circuit, in the sense there is a RB and there is a RE. There is no need of RC as such, because RE is there here, and when the transistor switches on, all the input gets amplified by the transistor and it is taken at the emitter. Now, how do we write a AC equivalent circuit for this particular common collector configuration? You can see at the right side, capacitor is short, so input directly comes to base to emitter. So, input is coming to base to emitter there is this beta RE, but the emitter is not grounded. From the emitter there is this capital RE. So, from beta RE there is this capital RE. And at the other side, output side, we have beta into IB. Actually, we can ignore that 1 plus beta as such, because I is approximately equal to IC. That is why this beta IB is directly written. And at the other side of the beta IB, it is connected to ground. Why? Collector is connected to VCC. VCC is nothing but AC ground. Now, similarly, at the input, RB is connected and the other end is connected to ground, because VCC is nothing but AC ground. So, we can see that RB is connected to ground here. Now, this circuit is slightly different from our earlier circuit. The reason is emitter is not grounded. Emitter itself is the output terminal here. Now, if we have to analyze this circuit in terms of AC, we have to find out the ZI now, input impedance now. Now, this input impedance is RB is there, and in parallel with that, we have this beta RE and we have this RE. Now, in this beta RE, the current is the base current itself, quiescent base current IB, or the AC base current IB. Whereas, with RE, the current is IE, because this current is the emitter current. So, IE is nothing but 1 plus beta into IB. So, now we will have to analyze this slightly differently. What we will do is, we will consider this particular impedance as ZB, impedance at the base, and then we will consider ZB in parallel with RB. So, we can define the input impedance ZI as RB parallel with ZB. ZB is the impedance at the base. Let us compute ZB itself now separately. So, at the input side, ZI is RB parallel with ZB. Now, how to compute ZB? ZB is beta into RE plus 1 plus beta into capital RE. How did we find it out? See, here it is IB coming and here it is 1 plus beta into IB coming. So, we have beta into RE and here we have 1 plus beta into capital RE. The voltage across this RE is 1 plus beta into RE. And the voltage across this base is nothing but beta into RE. So, beta into RE and beta IB is part of our pi model itself. Somebody is waiting in the lobby. Okay. Now, ZB is beta into RE plus 1 plus beta into RE. We can ignore that 1 there. So, we can simply write approximately ZB equals beta into small re plus capital RE. Now, when we write this way, we can simply find the expression for input impedance ZI is RB parallel with beta into small re plus capital RE. Therefore, ZI is RB parallel with beta into small re plus capital RE. This you will have to remember. All these formulae you will have to keep on telling again and again and again, and you will have to keep remembering these formulae. Only then you will be able to solve the exercises in the test and in the exam. So, there is no other way to remember the formulae. This is the only way. Keep on telling this formula 10 times and you will remember. For example, for a common collector configuration, ZI equals RB parallel with beta into small re plus capital RE. That way you keep on telling 10 times, you will definitely remember. Now, only when you remember, you will be able to solve the exercises. Okay, this is how we find out input impedance of this common collector configuration. Let us proceed with the computation of output impedance and the voltage gain. Okay. At the output side, IE equals 1 plus beta into IB. Now, this IB is nothing but VI by ZB. The quiescent base current or the AC current through the base is nothing but input voltage divided by ZB. Ignoring this 1 and replacing the value of ZB, we already know the value of ZB is beta into small re plus capital RE. So, let us ignore this 1 then I equals Vi divided by small re plus capital Re, because that beta gets cancelled there. The corresponding network, let us try to write a network for this particular expression now. That is why I told you analysis of common collector is slightly different from the earlier circuits, because emitter is not directly grounded here. So we will have to write a network for this particular expression. We can write the network like this. You can see Vi, then you have small re, then you have capital Re. Across capital Re, we are taking the output. Across the emitter ripples, we are taking the output. So we have written the expression here. IE is nothing but Vi by Re plus Re. So IE is the current flowing through this Re, and we can write it this way. There is Re plus Re, across that there is this Vi, and across capital Re we are taking V0, and the current is flowing through both of them. Okay. Now when we write this circuit, can we find out the output impedance? We can easily find the output impedance. Lokesh has raised the hand. Do you have any question? Ask me. No, maybe by mistake he pressed that button. Let me continue. Now, we got an expression for the AC emitter current using the circuit analysis. And we got this particular final expression. IE equals Vi by Re plus Re. Now we are writing a circuit for the same expression. Total voltage is Vi. IE is Vi divided by Re plus Re. And why have I written V0? Because we are taking output across the capital Re. Now, from the output, we look into the circuit. We have to find out the output impedance now. Input impedance is looking into the input side. Output impedance is looking into the output side. When we look from the output side, we will short this voltage source. You will be studying this in network analysis subject about how to replace the voltage sources and current sources when we do circuit analysis. So whenever we have voltage source, we should short it. When we short it, the small Re comes in parallel with capital Re. So naturally, output impedance is capital Re parallel with small re. So Z0 is capital Re parallel with small re. That is because when we look from the output side, voltage sources are shorted and these two are in parallel. So you can see that here in this case, output impedance is much lesser compared to our common emitter configuration. I have been telling you that we need an amplifier which will have a very high input impedance and very low output impedance and a very high voltage gain. Now in this common collector configuration, we are getting a very low output impedance. So out of the many ideal requirements which we have, some of them are available with some configurations. So we connect all of them later on as a multi-stage amplifier to get all our expected characteristics. So your Z0 is capital Re parallel with small re. Now let us proceed with the expression for the voltage gain. The voltage gain can be obtained from the shown network as follows. V0 is capital Re into Vi divided by small re plus capital Re. This network is nothing but a voltage divider network now. Now we want to find out V0 divided by Vi. So this V0 is across Re itself. So naturally, Re into Vi divided by small re plus capital Re. The total voltage across the network is Vi and we are taking the voltage only across Re. So Re into Vi divided by small re plus capital Re, this is V0. When you divide it with Vi, what happens there now? Vi gets cancelled. AV is V0 divided by Vi is nothing but capital Re divided by small re plus capital Re. Now we already know that the small re will be a few ohms, whereas capital Re will be a few kilo ohms. So what happens here? when this capital Re is the physical resistor which is present at the emitter, that will be a slightly larger value. Whereas the small r is the dynamic resistance of the emitter, that will be only few ohms. Now when you compare these two, the small Re can be ignored when compared with the value of capital Re. So in such a case, as Re, small re is much lesser than capital Re, AV or voltage gain is nothing but V0 by Vi, that is approximately equal to 1. And there is no minus sign here. In our earlier configuration, we had minus sign. Here we don't have a minus sign. Why? The flow of current in both the directions is the same. The flow of current is out of the emitter and the flow of current is into the base. Both are in the same direction. So there is no 180-degree phase shift and there is no need to put a minus symbol here. So AV is V0 by Vi approximately equal to 1. What does it mean? Now this means that the common collector circuit does not give voltage gain at all. If it does not give voltage gain, what is its advantage? It is giving a very low output impedance. The advantage of common collector network is that it is going to provide a very low output impedance, but it is not going to give voltage gain at all. So what we have to do? For voltage gain, we will use common emitter. And then later on, we will have one more common collector. And common collector will have low output impedance, which means we got voltage gain and we got low output impedance by connecting two circuits in cascade or in series. And then we can call it as a multi-stage amplifier. That is how we actually get multi-stage amplifiers. I have been telling you repeatedly that we will have a pre-amplifier, we will have a middle stage amplifier, we will have a power amplifier, something like that I was telling you. Now this is the reason why we have all those multi-stages. This is one of the reasons. Now because the voltage gain here is 1, the common collector configuration is also called as emitter follower. Why? Whatever is at the input, if it is coming at the output. Input is at the base, output it as the emitter. Emitter is following the base. Output is following the input. That means emitter is following the base or emitter is following the input itself because the voltage gain is unity. That is the reason this circuit is also called as emitter follower. As the voltage gain is 1, CC circuit or common collector circuit is also called as emitter follower circuit. Now, using this analysis, let us solve one exercise for the common collector configuration. So remember the formula. I am going to show you the formula once again. Zi is capital RB parallel with beta into small re plus capital Re. Please note down. Have that notebook and pen and please note down this formula. Zi equals capital RB parallel with beta into small re plus capital Re. And Z0 is capital Re parallel with small re. And finally, AV is nothing but capital Re divided by small re plus capital Re. We can approximate it to 1, but still for the sake of the exercise, we will calculate the value using this upper formula itself. So now, this is that exercise. Quickly, one of you tell me the answer. Exercise 13. Find Zi, Z0 and AV for the common collector configuration or emitter follower. R0 is given, beta is given, RB is given. You will have to find out what? You will have to find out small re. For finding out small re, you will have to find out this capital IE. For finding out capital IE, you will have to use the formula which we used for the self-bias circuitry at that time or common collector circuitry at that time. They had a similar formula as such. I am going to show you that solution now. IB is VCC minus VBE divided by RB plus 1 plus beta into RE. That is the formula which I had told you to repeat and remember. IB is nothing but VCC minus VBE divided by RB plus 1 plus beta into RE. This is the formula used both for common collector configuration and both for self bias in common emitter configuration. So in that way, we find out the value of IB, that is 26.86 microampere. Once you find out IB, you can find out IE, that is nothing but 110 into 26.86 microampere. Let us substitute that accurate value 1 plus beta for our sake. IE is 111, 110 plus 1 is 111 into 26.86 microampere, that is 2.98 milliampere. Now when it is 2.98 milliampere, small Re is nothing but 26 millivolts divided by 2.9 milli is nothing but 8.72 ohms. Now tell me the value of Zi. Zi is Rb parallel with beta into small re plus capital Re. Quickly somebody calculate and tell me the answer. Okay, Lokesh has given the answer once again. It is around 141.64 kilo ohms, means around 142 kilo ohms. Anybody else can give answer again? Okay, no one else is giving the answer. Let me show you the answer. ZB, first we have to find out ZB 110 into 8.72 plus 2.7K, beta into small re plus capital Re, that is 298 kilo ohms. That is in parallel with 270 kilo ohms. So Zi is 270K parallel with 298K, that is 142 kilo ohms. Good, Lokesh, you have given the correct answer. So Z is 142 kilo ohms. What is the value of Z naught now? Z naught is capital Re parallel with small re. So Z naught is 2.7K parallel with 8.72. 2.7K I have replaced at 2700 parallel with 8.72 ohms. So output impedance is 8.69 ohms. Now look at these two values. Zi is very high, Z naught is very low. That is what we had expected from any amplifier that is being satisfied with this common collector configuration, which did not get satisfied with the common emitter configuration. It was not satisfied either with base bias or with voltage divider bias. But whatever was expected, those two things were satisfied in common emitter configuration. But the last one, voltage gain is 2.7K divided by 8.72 plus 2.7K. Capital Re divided by small re plus capital Re, we get around 0.9968. It is almost equal to 1. Now this means that we are not getting the voltage gain at all. That is why I have been repeatedly telling you, we are going to combine multiple configurations for getting our expected behavior of the amplifier. That is called cascading of the stages, or that is also called as multi-stage amplifiers. But we have not kept it in the syllabus as such, because there is no point in discussing all those circuits now, as they are all obsolete as far as BJT is concerned. They are still there as used with the MOSFETs, and you are going to study MOSFET in much larger detail when you come to third year, because MOSFET is slightly difficult to understand compared to BJT. That is the reason in the second year we are covering BJT, so that you will be familiar with the circuit analysis of AC and DC. Whatever you learn now, the same concept you are going to apply with the MOSFET also when you come to third year. So that's it now. We have seen how common emitter configurations AC analysis is performed, and we have seen how common collector configurations AC analysis is performed. And we have seen that in the common emitter configuration we get voltage gain, whereas with common collector configuration we get larger input impedance and lesser output impedance. That way, whatever we had expected from an amplifier is satisfied by using both of these configurations. With this, let me end the class now. In the next class, I am going to discuss the common base configuration, and we will solve some exercises using this common base configuration. And later on, I am going to proceed to the very last part of this module, that is called hybrid parameters. Just like we had this RE model where we used the dynamic resistance of the emitter for modeling the BJT. There is another model which is similar to this RE model, that is called hybrid model. We are going to discuss that model in the next class. So I am going to end today's class. See you in the next class. I am going to post the attendance link in the Google class.